Right. Before we go into DBMS architecture, just thought I'd show you the implementation of division in SQL. SQL does not have a division operator, so we have to do it like this. So it's kind of using it is using the same kind of strategy, but you can't express it in such a simple way in SQL. So one thing we're doing, we've got a correlated subquery. So something like this effectively says, for each beer B, do the following check. Generate the names of all bars, which is obviously what that's doing, and then generate the names of all the bars that sell this particular beer. So sell the current beer B. And I guess if I don't need that, but just to be consistent with the rest of the thing. So find all of the bars that sell this particular beer, which is the next beer in, if you like, the iteration through all the beers up here. Then work out the difference. That's all bars, that's the bars that sell B. If I take the difference, and if the beer is sold at all bars, then the result of that difference should be empty. Okay. So any beer that's sold at all bars will generate an empty set as a result for that. And the way that you can check for an empty set in SQL is to simply say, does there exist some tuple in this set? And if in case there's no tuples, then we're interested in not exists. So that gives you the same effect as doing that division, but it's a little bit more obscure to express. So I'm pretty sure there was an example of that back when we originally went through all the SQL stuff in the beers and bars database. Alright. So, DBMS architecture. Why are we talking about DBMS architecture? That's not COMP3311, it's not on the course learning outcomes or anything. That's done in 9315. However, knowing a little bit about how DBMSs work can sometimes give you clues to improve the efficiency of queries. If you write a query and discover it's too slow, what can you do? I'm sure some of you are bumping into that on assignment 3. I've extracted all the data I need using this query, but it exceeds the time limit. What can I do? So if we understand a little bit about how they work, we might have a chance of fixing it. And also, another important thing, since DBMSs are inevitably used in a multi-user environment, so concurrency is an issue, we might need to enforce locking ourselves to make sure that that there are no concurrency issues. So DBMSs obviously try to do some of this stuff. The query processing part of a DBMS is going to attempt to organise the execution of the query or the evaluation of a query so that it's reasonably efficient. It's not going to, do everything as a product and then a filter and then a projection, which is a simple-minded way of translating SQL statements into relational algebra. So I'll try to do it in a slightly smart way. Whether it does it the way we want or not is another matter. And it will also try to handle concurrency using built-in transaction processing stuff. But we have to make sure that we tell it, here's the start of a transaction, here's the end of a transaction. So when you're dealing with a DBMS, sometimes it's a bit annoying that the database tries to do so much for you and tries to do it in a way that you don't necessarily want. So query processing, maybe we need to somehow subvert what the database is doing, or at least express our queries in such a way that we're encouraging the DBMS to produce an efficient implementation. And similarly, if we know how transaction processing works in the database, we might be able to structure our transactions to make sure that they're all right. All right, so what have we seen? You know, you go into PSQL, you type a query, and you get some results. That's all we've seen so far. We don't care what goes on inside the black box, but I would like to take a little tour of that black box now. So one way you can look at a database query evaluator is that it's a relational algebra virtual machine. So you feed in a bunch of relational algebra operations, and the database engine will execute each of those in turn, and maybe pass the results of an earlier relational algebra operation onto a later one. Now, while it's nice to think that we've got selection and projection and join and that's all we've got, in fact, DBMSs provide multiple implementations of selection, maybe not multiple implementations of prediction, yeah, it could well do, and multiple implementations of join. And some of them will be efficient in certain contexts, and others will be more efficient in different contexts. So it really has to choose the appropriate version of selection for the query that you've asked. And of course, you might want to make sure that you ask your query in such a way that the database will choose a particularly efficient version of a relational algebra operator. Alright, so how does the whole thing fit together? Like this. So we've got a top level which parses your query and evaluates it and produces the result. It calls on a query execution module which calls on the relational algebra operators, which need to access the data on disk, so they have to understand how the data is structured on disk and what ways you can access it. And inevitably DBMSs run through a buffer manager. If they didn't have buffering, they would be excessively slow. And finally you reach the data on disk, you get it back in chunks through the buffer manager, and it filters its way all the way back to the result. So what we were just looking at in the last hour was relational algebra operations, and they exist, sort of at the middle level of the DBMS. And of course, sitting alongside everything and making the code 10 times bigger than it needs to be, concurrency control is extremely important. If you didn't have to worry about it, DBMS code would be a lot smaller. But there it is. So 9315 looks at all of that. 3311 is just going to look at it a little bit, enough that you can make some choices about how you implement your SQL statements and know that they're not going to end up being executed inefficiently. Alright, so let's open the black box up and have a look at what happens. We sort of opened the black box up here, but if we go here, so the query is a piece of SQL, it's a piece of text, it's got a certain structure. If you've got a structure, you can parse it and work out what it looks like. And what the SQL parser will typically do, and certainly this is true in the case of Postgres, it'll produce a relational algebra expression in some internal format. It won't necessarily look like what we had on the earlier slides, but it's definitely a relational algebra expression, which involves selections and projections and blah blah blah. It then runs that through an optimizer which will convert that expression into a sequence of operations that will give you the result of that expression. And in doing so, it has to worry about the different possible implementations of selection. It also has to worry about the order that you execute the operators in the relational algebra expression. So at this point we've got if you like, a sequence of relational algebra operators like we had on those earlier slides. So then you feed that in like a piece of machine code into the database engine, and it generates a bunch of tuples which are then run through something and displayed as a table like we see in PSQL. Of course, these tuples could be siphoned off by a program as well, like you're doing with assignment 3. Alright, so how do we go from a piece of SQL to a relational algebra expression? So here's an example. So we're doing a join on two tables. We've got a where clause and we've got effectively a projection. Right, so these operations have to appear at some point in our sequence of operations. So let's say, for the sake of argument, that we do the join on RNS first. That's a pretty straightforward translation of what we've got here. We then do the selection, filter out all the tuples that have d equals 100. We then project out just the A column, and then we rename it as X. So that's the set of relational algebra operations that will be produced from this. So normally a select clause becomes some kind of projection operator, a where condition becomes some kind of selection condition. Whether it's a single select or whether it's multiple selects that somehow get put together is up to the query optimizer. And typically what you've got in the from clause is a join. Now, of course, you can write things like this example up here. You could write select A as X from R, comma S, where D equals 100 and R dot B equals S dot C. So it's an alternative way of writing that join, which is slightly less obvious, but it's going to end up being translated to the same thing. So that's the reason I said a where condition could become a straight selection operator, or it could become a join operation. Alright, so that's what we ended up with from a fairly straightforward translation of that. Can we do better? And better basically means more efficient, which means less data being shunted around the system. So it's pretty clear that this is going to produce maybe a fairly large table, and only some of the tuples in that table we produce are interesting. Potentially, we could filter these interesting tuples out before we do the join. And if we did that, then it's likely the inputs to the join, or at least one of the inputs, is going to be smaller, and the output from the join is also going to be smaller. So let's say this produces 1,000 tuples and then filters down to, say, 10. If we filtered this to 10 in the first place, then the output of the join would be size 10. So quite a difference there. Projection and renaming, well, you can't do much. And in fact, in Postgres, projection is kind of bundled in with this, with the operator. You're specifying what the output is supposed to look like. So to some extent, it's doing a little bit like what we do there. So I would argue that a better approach to this, which is going to be more efficient to execute. So rather than doing things that way, would be to do the selection first. So you're cutting down the number of tuples. Now another, alright, you can't get rid of any more. If we didn't need A, in theory, if we were doing everything on B, in theory we could do a projection at this point and reduce the size of the output tuples. But if you think about it, we need all of the other. No, we don't. We don't need D. So in theory, we could do a projection at this point. So we end up with smaller tuples because we don't need D once we've used it to filter the original set of tuples. All right. So then we could do a join and produce A, B, C, where we join. That came, where'd you get temp1 from? The Raven. D came from S, I think. So we're doing the selection on S, and then we join R. Okay. Hopefully that's right. Yeah, I'm pretty sure it was R, A, B, S, C, D. Alright, so then all we got to do, well, we can't really change these too much. temp3. We do that same projection, and then the rest is the same. If you really want to notice that what we've done here is we've got a implicit projection going on. If you don't like that, given that we've got an explicit projection down here, we could potentially bundle that in here, and you could even do an extra step if you really wanted to do things that way. Right, but the really critical thing is we do this selection first, cut down the number of tuples that we need to consider in subsequent steps, or at least in this step here, and then do the join. We're doing a join on maybe R is a large table, maybe S is a large table. We're then doing a join on a large table and a small table. Various join algorithms can actually do that very efficiently if you're dealing with a small table and a larger table, giving you a final result. And notice all these intermediate results are smaller than the ones we were dealing with before, therefore the size of the data is also going to be smaller. And of course when we do the projection we end up with very small tuples containing a single value, and then we can do this rename to simply for changing A to X. So it can make quite a big difference depending on the order that you do the relational algebra operations. I didn't do a hard analysis there saying this table is this size, this table is this size. Doing the selection produces something this size and so on. I didn't do that, but if I had, it would have been even more stark. Alright, here's another example. This time we have to throw in some extra, yeah?
On the last exercise, when you did the first temporary table, how did you end up selecting the B, C, and D, or projecting B, C, and D even though the selection
Oh, thank you. Because I'm a donkey. What do I need? You are correct. I don't need D, I need an A. Yeah, right. So that's what I
But if
should.
you select from S and it only has 2 columns, can you do that?
Oh, you are correct. Good point. All right. So I don't need to. Yeah, thank you. I'm talking rubbish. Good. Because you picked me up on. All right. Is that right?
I think S only has C and D.
Oh, all right, it's not right. Right. And R has B, temp 1 has C, so that join can happen, etc., etc. Yeah, good point. All right. So then, yeah, the argument still applies that the result of that select is going to be relatively small. So potentially this join is now more efficient than this big join up here would have been, and the rest follows on from that. That's not going to change. All right. Well, it will change a little bit because in this example up here we had 4 attributes in temp 2. Here we've only got 3. So the projection's dealing with less tuples. Right, so to do something like this, we need to introduce extra extended relational algebra operators. So imagine that we've got a group by operator that can take a table. So remember, all these operations produce a table. So we've got a table, we can group it by ID, and then we can do some kind of selection based on the whole group. And in this case, we're checking how big the group is. And if it's greater than 100, then it gets selected. And then we simply grab out work anyway. If I fed that into SQL, it would complain. Oh, well, I can't modify this. All right, I better modify it to make it kind of correct. So let's call it ex2. Why is that not going to work? What error am I going to get from my SQL parser? It's going to complain that I don't have s.id in the select clause. So if you're doing a group by, what you're grouping by has to appear in the select clause. So I can't do what I've done. That would produce an error. But what I could do if I'm going to do that, I need to do that. And okay, that would be plausible, I think. And notice here I'm using implicit joins. So I'm just mentioning all of the tables, and these conditions in the weak clause are actually join conditions. So if I really wanted to, I could rewrite that. Using explicit joins, how you lay these things out is largely a matter of taste, I think. Then you wouldn't need to wear cords at all. So you could put explicit joins here. Something like that. Hopefully that's correct. It won't necessarily give us distinct codes, so I think we'd need another wrap around this to get rid of that. So we can turn that into a view and then do select distinct code from that view. Alright, so in that case, alright, I will have to go through and fix them because they're clearly not correct. And I guess there's no point doing an exercise on a bunch of not correct stuff, so we won't. Alright, so one of the things that the DBMS has to do in deciding on what order to do relational algebra operations is to work out how much is it going to, or how long is it going to take if I do it this way versus how long is it going to take if I do it that way. And that gets into the whole notion of cost estimation. So the cost of running a query basically depends on the sequence of operations that you've specified in the query execution plan. It depends on the size of tables, and in particular it depends on the size of the intermediate tables that you produce, those temp 1, temp 2 things that I've been using. And then how fast you can produce those temporary tables is affected by the kind of implementation of operations that you've got available. So do you have an index on a table? Is there hashing available on a table? And so on. And also it's determined by the amount of buffering you've got available as well. So if you want to analyse the cost of a query, you've got to analyse the size of the intermediate results and then work out how much each operation is going to cost based on the size of its inputs. And ultimately, everything in databases comes down to the fact that trying to get data off the disk is very expensive, is the most expensive operation in the system. Everything else that happens, evaluating conditions on tuples and so on, the cost of doing that dwarfs into insignificance relative to the cost of fetching data from disk. The other thing about the way databases work is if you need a tuple, you can't just fetch one tuple from the disk, you have to fetch an entire page of tuples. So that can also obviously impact the overall cost. Right, so once the query optimiser's done its job, it produces a sequence of relational algebra operations, but they're not just any old relational algebra operations. They're ones that have been specifically chosen for this execution plan. So for some reason the database knows that using a hash join to solve this particular join is going to work well. It also knows that when you come to producing temp2, then using a sort merge join. It's still a join operation, but it's implemented differently, and the system works out that using that particular implementation of join is going to be better than using a hash join for it in this example here. Binary search, linear search, what else have we got? Oh, searching in a B tree. Okay. So all these different kinds of implementations of the various relational algebra operations come into play, and all of these plans, hopefully, are going to produce the same result, but the cost of getting to that result might be significantly different between all three. And just a quick note about what kinds of implementations of relational algebra operations there are, and if you've all done COMP3311, that kind of thing should be no surprise to you. What's interesting, right? Hashing can be done very efficiently, but is only useful if you've got equality tests involved in your condition. There are various flavours of join that have different performance characteristics, various flavours of selection that have different performance characteristics, and so on. Right, so how do we go from an SQL query and a simple translation of that to a relational algebra expression into a query plan that is hopefully efficient? So, and I've kind of given away what's the best method. The most efficient method is probably the best method, where efficiency is determined by how long it's going to take to run, and that's predominantly determined by how much data has to be transferred backwards and forwards from between disk and memory. And so relational databases have a query optimizer built in. Postgres has certainly got one. SQLite, I don't know. Maybe it does, maybe it doesn't. And so a query optimizer basically takes in a relational algebra expression and produces one of those query plans, and hopefully it produces a query plan which is efficient to evaluate. Right, so it's a standard sort of minimization type approach. You've got a best cost, initially infinite, a best plan, you've got nothing, and basically the simple-minded approach is generate all possible query evaluation plans. For each plan, work out or estimate how much it's going to cost, and if the cost you get is better than the best, the one that you've seen so far, then this plan is better than all of the other plans that you've seen so far, and you just remember that accordingly, and eventually you return the best plan that you saw. Now that's all very nice in practice to say that, but for any given relational algebra expression, there are potentially extremely large number of plans that you could possibly generate. Not just the order that the relational algebra operations are done, but which particular flavour of that relational algebra operation is used. So, the combinations blow out quite dramatically. So, it's generally not possible to work out an optimal solution. So, some query optimizers will be a little bit smart about the order that they generate evaluation plans, and they'll try to generate evaluation plans in an order that they think the most efficient ones are likely to occur early on, and then they'll cut off the search after a certain length of time. There's clearly a trade-off going on here, that if you spend so much time doing your optimization that the cost of the optimization exceeds the cost of evaluating the query, you're not really getting ahead. So relatively cheap optimization costs, do it as fast as you can, and get a decent evaluation plan, and then execute that plan. So that's the deal. Okay, so that's all very nice. That's what the DBMS is trying to do for you. You can make its life difficult by writing your queries in certain ways, and so it's worth taking a look at how we can write queries to avoid these kind of problems. if you really want to, optimize the cost of a whole database application, one thing you've got to look at, what kind of operations are executed frequently? Does it quite often do this particular select? So we're going to be on a win if we can make that particular select efficient, if that's the kind of operation that happens 90% of the time, for example. You can then have a little bit of an impact on what the query optimizer does based on the way you express your query. And so if you push it in the right direction, that's good. How much each implementation will cost? Well, we don't really know as an SQL programmer what the database is going to do or how much it's actually going to cost for each implementation. We can observe after the event, and I'll have a look at that if we have time. So one thing you can do to make queries generally more efficient is to add an index to a table. So if you're doing particular kind of searches, an index could make those particular kind of searches much faster than a linear scan of the table. And also, you can help the database out by avoiding certain query structures that force the optimizer to go in a certain direction that is less than optimal. So how you express your queries, creating indexes on tables are really the two, if you like, weapons you have in trying to make your queries efficient. Ooh. And that's an example of what we did earlier, where we did the selection before we did the join. If you apply functions, so if you say something like select star from table R where attribute A divided by 2 is greater than 4, that's potentially going to be less efficient than saying A is greater than 8. I don't think a lot of database expression evaluation things are smart enough to rewrite that like something like an optimizing C compiler might do. Indexes are nice for querying, but they do impose a cost on update. So every time you add a new tuple to a table that has an index, you have to update the table data itself, but you've also got to update the index. So there's 2 bits of work. So if you're doing something like a log table that you're not really going to query very often, it wouldn't make sense to put an index on it, because every time you add an entry to the log table, you've also got to update the index, which is hardly ever going to be used. One thing to notice about Postgres, which you might have already noticed, every time you define an attribute as a primary key, Postgres will create a B-tree index on that attribute. So that helps with doing joins and searches on that table, certain kinds of searches. Let me see. So what you do as a database application programmer, sure, you write a query, the query optimizer gets hold of it, munges it round as much as it can to try and make it efficient, but you don't really have super amount of control over what it does. You can certainly block it from taking certain choices which would lead to efficient evaluation. So let's have a look at some examples. Nested queries are generally a bad idea, so try to avoid them where you can. I noticed some of the textbooks start out by their initial introduction of SQL using nested queries. Often nested queries are relatively easy or easier to understand than doing it with joins, but so here's an example. Want to get the name of every employee whose salary is greater than 50,000 and they come from the sales table. Now, of course, that'll work, right, assuming you write the query right, but of course the way you normally do it is you do a join on the employee and the works in table, and then you filter out just the ones from the sales department. It might be less obvious that this is happening if this thing happens to be implemented via review. So you might have select create or replace view sales employees as that particular subquery there. And then you say where employee in sales employees. And you think, that's a nice simple expression, it makes sense. Trouble is, views, as I've mentioned a couple of times, don't actually get executed as separate things, and even if they did, it would still be bad. But creating this as a view basically means that at query evaluation time, the query process is going to take your select from sales employees and expand it to this anyway. So you'll end up with that. You'll end up with a query just like that, even though it's expressed using a view. So one possible way that the query evaluator might work is to do that and then do a check whether that particular employee is a member of that set. Now, if that set is quite large, then the cost of doing this for each employee is slightly painful. And the standard, like I said, the standard way of doing that would be to do a join. The join can be potentially more efficient, certainly is likely to be more efficient than doing that. For one thing, you're running through the entire set of employees, but you're just pulling out sums of them. Why bother running through the full set anyway? Just start by filtering out just the employees who are in the sales department. So if you write your query like that, it's likely that Postgres, well, Postgres might be a bit smarter, but a lot of query evaluation engines will implement something like this, which is relatively inefficient. So yeah, you could do it using a join. It would be more efficient generally. The other thing about this join is it's not necessarily going to be doing a join on the full employees table and the full working table. It might actually apply this condition to the works in table before it does the join. So you'll end up with a relatively small table as part of the join. I don't know why I would use that strategy, but there you go. Looks like I've got a bit of fixing to do. Here's an even worse expression of the query. All of these will produce the correct result, but they're going to take a lot of time to do it. Alright, so it's 5 to 4. Let's stop talking about this and